Hello. Please ask me. It is audible.
Yes, sir.
Yes, sir.
Great.
Okay, sir.
You know, transformer here we discuss the single phase and three phase. You know, like mostly working principle are same. There is a three coils in three phase transformer, three primaries, three secondaries. But in single phase only two windings, one primary, other is secondary. Primary means which is source side, secondary means load side. Now maybe HVLV, actually technical terms we use HVLV windings. Now maybe LV is primary or HV is primary, step up and step down transfer. Like this is an AC device, why? Because it work only on AC, which is used to change the voltage. Means to change.
Sir, are you sharing your screen? Because
Sir,
we
आपका
cannot
screen
see
share
this.
नहीं हुआ है.
Oh, sorry. Today we did the transformer.
Yes, sir.
So it is an AC device which is used to change the voltage. Means high voltage, low current. If voltage is high, current is low. Okay, like primary side. Then on secondary side is voltage is means into low voltage and high current, because this transformer, why its name is because it transfer the power from primary to secondary, or means from one circuit to other circuit, secondary circuit, at constant frequency. Okay, without change of frequency. In brief, we can say, so there is a two electrical circuit, they are isolated electrically, but mechanically, electrically they are coupled. Okay. So this transfer the power from one circuit to other, that is without change of frequency, and it is accomplished this by electromagnetic induction, where two electric circuits are mutually inductive and influence to each other. See, like this is the principle of mutual induction. Here there is a two coils. One is connected to AC source. Like here is a 2000 volt RMS value. This is the primary one because it is source side. On secondary, we measure the potential, open terminal potential, induced voltage. So if two coils placed nearby, if one is connected to changing, means alternative voltage source. Alternative means its magnitude and direction it change with respect to time. Okay, so you know, if we apply the sinusoidal voltage, sinusoidal current is flow, that produces sinusoidal flux, changing flux, that link with secondary also. So there is a rate of change of flux. So due to rate of change of flux, according to Faraday's law, there is a induced EMF. So here with principle of operation of transformer in mutual induction. What is the mutual? There is a two coils. Suppose a coil 1. Second is this coil. They placed here. This is coil 2. Here suppose N1 turns. Here it is N2 turns. Okay. When this primary, it is connected to alternating AC source. Then there is a changing current, alternating current is flow. So you know, my dear, flux is directly proportional to current. Okay. If current is sinusoidal, so the flux is also sinusoidal. Okay, sinusoidal current produces sinusoidal flux. Okay, maximum flux, sorry. Here it is a maximum flux, okay, phi m. Now what is the equation of this? So phi equals to phi m sin omega t, correct? This it is sinusoidal flux. It means there is a rate of change of flux. Okay, so the flux produced by, you know, if a circular coil produces a straight magnetic flux, so these flux lines are like this. Okay, like this. The induce in the, so see the flux produced by this coil, suppose phi 1 by I1 current, correct? Then it linked with this coil 2 also. So if we measure here potential along with this conductor, okay, with galvanometer, okay, so there is a induced voltage E2. Maybe there is a self-induced EMF E1 in primary, okay, this is V1. Here it is E2, okay, correct? Or V in small letter you write induced voltage E1, E2. So you know E1 equals to, it is self-induced EMF d phi by dt, okay, d phi 1, because flux phi 1 is linked with itself, the coil. So there is a self-induced EMF. But E2 is mutual induced EMF because it is in coil 2. Okay, 2 to N2 number of turns, but same flux. Rate of change of flux is same. Okay, so this is the self-induced EMF induced in primary, and this is the mutual induced EMF. Okay. In primary. Okay. Now, actually, why this negative sign is come? This is due to Lenz law. Actually, according to Faraday law, this induced EMF is directly proportional to rate of change of flux. okay, or E equals minus and so d phi by dt, number of turns. But why is it negative? Lenz law. Lenz law. What is the Lenz law? It states the polarity. Faraday's law states the magnitude of induced EMF. It is proportional to rate of change of flux. Okay, correct. But Lenz law is what is the polarity of induced EMF? It opposes the polarity of induced EMF is such that it opposes the causes by which it is produced. Means it is opposite to the applied voltage. Correct? Okay, dear. So this is the prime mutual inductance principle. Now we come to the transformer. Continue. See, so like this is the transformer. Here there is a primary and second is load side. Then suppose the N1, N2 number of turns in primary, secondary. Oh, okay. Then there is a flux change is same, but these are the induced EMF in primary and secondary. Okay. Now constructional detail. So if there is a two type, cell type and core type, this is the core type. Here you know this is the laminated core. Over this laminated core there is a LV-HV winding. Actually, by to understand the working principle, we show the winding. Primary means HV on one limb and LV on other limb. Correct? But it is not like that. Physically, see, first we put the half LV on one limb, then half an other limb. Then over this LV, we put the HV, half of HV at other one side, half of HV on other side. Why we do this kind of? Hello? Why we overlapping the primary and secondary means HV, LV? So there was one question is asked in your examination. Some person is also asking of that question also. Okay. There was a question in your examination. Yeah, I think it is September itself. It is asking magnetic flux December. Yeah. Yes. Now this is the question. Please discuss the magnetic leakage in transformer and indicate how its value may be kept down. So what is the leakage, magnetic leakage or magnetic leakage reactance in transformer? Magnetic leakage means leakage flux. And how we can minimize this? And we explain with vector diagram how this value is affect the voltage regulation. Okay, dear. We are discussing on this. So see, one of the reason of this also for better means mutual induction. better coupling between this primary and secondary or HV/LV, so that the flux produced by primary is a 100% link with secondary turns or other coil. Okay, so interleaved coil, that is called interleaved or overlapped. Okay, so this, hello, here it is shown LV. Over this LV we put the HV winding after insulation. Okay, correct. Now see here in cross section view, it is simply seen. See this light gray color, it is primary LV in cell type. This is your cell type, this is your core type, and here over this LV we put the HV windings. Okay, same here is LV, HV. Here is also half LV, then half LV here, then over this LV we put the HV winding. Okay. Now question is come, why we put a HV after the LV or over the LV? Why we put LV winding first? Hello? Yeah, any reason please? Hello?
To reduce magnetic leakage.
मैग्नेटिक लीकेज तो तब भी रिड्यूस हो सकता है जब हम उसको वी कैन इंटरचेंज, मींस फर्स्ट वी पुट HV देन ओवर दिस LV, वो तो इंटरलीव्ड है तो ओके. But why we select, we first put LV winding over this LV we put HV? There is a 3-4 reasons I will tell you. First, HV means high voltage, correct? So if it is outside we can properly insulate, like it may be 6.6 kV or it is 11 kV. Second, tape changer, you know, we use a tape changer to control the voltage fluctuation on transformer. Just a minute. Okay, so tape changer we put on the hello, audible?
Yes, sir.
Yeah, so actually the tape changer we prefer to install on tapings we provide on HV, because HV has a large number of turns as compared to LV. So number of tapings we can easily provide. Okay, and see, taping means we take a connection. So if your HV is outside, it is easily accessible, na? We can access easily. Next is reason is other reason. See, HV means high voltage. So high electrostatic fields are there. High electrostatic field. Due to this, there is electrostatic force produced in the core. They deform the core. That's why if we put at distance, some distance, means first we LV then HV. Okay, then this forces may be reduced, and then your core may be not deformed. You know, due to electrostatic force, when we pass from a transformer, it created some humming the sound also due to this force only. Okay, so if like cable, HT cable, why we put a grading of insulation? Because near to conductor, high voltage strength, high stress is there. That is called voltage gradient. Voltage gradient is high. Okay. Same like here. If high voltage coil close to core, then there is a high voltage gradient or electrostatic force are there. Get my point? Hello? This is the region. That's why we put HV after LV. Okay? Got it?
Sir, last point explain again, sir, please.
Suppose, in everything, suppose this is a cable conductor. Over this conductor, we put insulation. Okay? Over this insulation. So, the voltage stress close to conductor is higher. Close to conductor. Then it is reduced. Okay, actually, if we see the voltage stress from surface of conductor, it is from surface. Gradient means voltage gradient, like from surface, and this is your thickness. So at higher value, it is highest here. Then it is decrease. Okay, like this. So as distance x is increase, and this is a G. G means voltage gradient. What is the G? G is nothing but it is volt per meter. Volt per meter gradient. Okay. So at 0 means at surface of the conductor, at conductor surface, highest voltage. As this distance is increased, it is decrease. Okay. So if high voltage coil, same like if this is your core, then if you put the HV winding first. So high voltage stress will be there. They deform the core. Electrostatic force will be developed. Okay. There is an electrostatic force, magnetic force is there in magnetic field. In electrical field, electrostatic force are there due to voltage gradient. Okay. Now, come to the major region. This is the region, but our question is this: to reduce the magnetic leakage, correct? Now, stamping. Now, second point to reduce the leakage flux. Hello, we use a multi-stepped core. You know what is the multi-stepped core? There is another reason we use a laminated core. Laminated means this we use a thin sheet. Okay, to assemble this core, like these are the plates. See here, a single plate like this. This first plate. It is like this when we make a core. Like this kind of number of plates put together, like here, okay, like this, okay, like this, correct? Then we make this thickness of core, okay, laminated core. Why we use a laminated core, my dears? To reduce the eddy current loss, core loss. So there is a two magnetic loss, hysteresis loss. Hello. There is one another question also in ETO. It is earlier asked losses in transformer. So there is a core loss, and copper loss. Correct? Copper losses due to in primary and secondary resistance. Got it, my dear? Sorry, 2 I2 square R2. This is the copper loss due to primary and secondary winding resistance. But core loss means, or iron loss. It is 2 types. First is hysteresis. Hysteresis. Is loss, and the other is eddy current. Okay, the eddy current is actually also, it is I square R loss. Due to this, it is a iron core. So you know the EMF is induced in the coil, also induced in the core also, because it is also conductor, iron. Then due to this core resistance, there is a I square R short circuit currents. Due to this short circuit current, there is a, this losses are there. So how to reduce this eddy current loss? By lengthening reduce this current. How reduce? We put we not make a solid core. We make a laminated, and we put the insulation between these two plates. Lamination, we put the insulation. Okay. So now we cut we chop this current. So this value is reduced. So these losses are reduced. Okay. Correct. Second hysteresis is due to we use a soft iron, means high permeability core. High permeability material core we use, like CRC, cold roll grain oriented. CRGO, silicon steel core, laminated core. Okay, so which is easily magnetized and demagnetized. Okay, soft magnetic material we use. Okay, very good magnetic material is ferrite material. Ferrite. Okay, correct. So this is the losses. So now laminated. But my dear, here, you know, actually, if same dimension, or we make if we see now the cross section area of this core here, cross section area, if we cut, then it seems like, hello, it may be square type. So this is the lamination will look like this. Okay, when we put a winding over this, this is a square core. Okay, there is a ear gap. Due to this ear gap, there is a leakage flux. Leakage flux. When there is a leakage flux, due to this leakage flux, there is a leakage reactance. You know what is the leakage reactance? Inductance. Hello? Inductance L is nothing but it is total flux linking per unit current. Okay? Suppose a coil is there. There is a number of turns N. You know, when current is passed through this coil, okay, I. So this current is multiple, number of times. Number of times it is multiple. Then there is a flux. Okay, flux is produced here. Number of times. Correct. So total flux linking, not leakage. Here it is link. Okay. Per turn flux is phi, then it is N phi by I. Okay, this is the formula for inductance. But when we calculate a leakage reactance, first we calculate leakage flux. Magnetic inductance means magnetic flux. Leakage, magnetic leakage. Magnetic leakage means leakage flux. Okay, magnetic flux. Okay, if we calculate leakage flux means which is the leakage flux apart from this core. Actually, maximum flux is passed through this core, because which is produced by primary. If there is a winding, you know, there is a winding on this core. If there is a winding, when we put a current, maximum flux pass through this core only. Okay. But there is a some effect that is called franking effect. That is, some is like this. Okay. Here also some flux is like this. Okay. I will explain. So this is your transformer core. That is, this is the primary winding. When we put a AC source, there is a current. When this current is passed, please you write the right hand rule. See, this fingers indicate the direction of current, then flux is upward ना here. इस core में flux कैसा होगा? Upward होगा. Okay, correct ना? Flux is like this here in this direction. Okay, so it take a means your flux is, this magnetic flux is circulate within the core because it has a low reluctance part is provided. This is a iron core. Iron core. It provide a low reluctance path. Low reluctance path means flux is easily flow. Like a conductor it is easily flow of current. But here in magnetic material, flux is easily flow. Okay. But now some flux, some part of flux, it is circulate here. See here, like it is here. Okay, like this. So this is called as a leakage flux. Here also in secondary coil also. Okay, like that. Due to this, there is also leakage flux. Okay, so this total flux we calculate, that is called leakage flux. Suppose this is phi L, total leakage flux. Then if we calculate leakage reactance, inductance, leakage inductance we calculate. Inductance. Okay, so it is L, your leakage flux per unit current. This. Okay, that is it is in Henry or millihenry, whatever. Then we calculate leakage reactance. Hello. Due to this leakage flux, there is a leakage reactance that is denoted with XL, leakage reactance. That is nothing but it is omega L. Correct, na? XL equals to omega L. It is in ohm. Okay, dear. In both primary and secondary. Okay, dear. Leakage inductance, then leakage reactance. Okay. Now we come to the question. How we reduce? First is interleaved coil. Then maximum flux is link. Second, see, we reduce this ear gap. How we reduce? So apart from this single dimension, we use a multi-dimension core. Okay. So multi-dimension means like a cruciform core we have this. But here in cruciform, this lamination is different dimension. Okay. So if like it is a two-stepped core, there may be some multi-stepped. Now see, this ear gap is reduced. Okay. So see in the diagram, hello, multi-stepped like this here. Okay. Then this ear gap is reduced. When ear gap is reduced, then leakage flux is reduced. Okay. Correct. First, see, these coils are interleaved. So by hello, what are the factor you design? First, overleaved coil. Second is multi-stepped core we use. Okay. Now how it is affect we later we discuss also. Now you come to the working principle. So see, like this is the transformer. When we put connect this primary, sorry. When we connect with primary, the EMF, the flux is produced, which is confined within this core, soft iron laminated core. Then this flux is linked with secondary, so there is a induced EMF, mutually induced EMF in secondary. Okay, so when the current in the primary coil change means being it is a alternating in nature, there is a changing magnetic field is produced, set up in the core. Now due to this rate of change of flux with primary as well as secondary also, so there is a induced EMF in secondary. Okay, mutually, correct? Like this is the to explain with working principle, there is a number of turns N1, N2, then induced EMF and E2. This is connected to primary side, this is load side. Okay, so this is the your simple diagram to a transformer which is showing the both winding and source and load side or core, magnetic core also. Okay. So this both coils are coupled with a common magnetic core. Now, okay. So now we come to the this page. Okay. This is your suppose primary winding. Yeah. This is secondary side. Now this is connected to your primary source, means this is your alternating source. So here this your voltage is V1, suppose applied voltage. It is a single phase transformer. We discuss core type of. Now there is a current is flow. Suppose it is at no load. Here it is no load, open. Your secondary is open. Then this current, set up a flux in the core. Okay. So see, this core is flow like this. Okay, in this core. This is your magnetic core. Here flux direction is this. Okay, because you just apply the right hand rule, this finger in coil, finger indicate the direction of current and your thumb is indicate the flux. Okay, like if straight conductor, if this is a conductor, straight, if your current is straight, it produces circular magnetic field. Like see, this is your conductor, suppose. This is your conductor. So in this conductor, if current is straight, so how the flux will be circulating, you know, correct? This is your flux. So see, if this is your conductor cross section, here is current is enter, we show with star point, like a cork screw rule also we apply. Here, suppose current is outward, here is inward. So here you also apply this either your cork screw. When we rotate now, we tight the screw. So your clockwise direction. This is show the flux. Your flux direction is this side, clockwise. Okay, like here to here. Okay, but here outward now. So this is your current is outside. Flux is magnetic flux is anti-clockwise, correct? But when we talk about coil, suppose this is your magnetic coil. If we talk about this, okay, this is the iron core. Over this we put a winding. Now here, suppose this is positive DC source, we connect. Now this current is flow. So here this is the direction of current. Then flux will be this. It comes like this in the straight magnet, like bar magnet, like. Hello. So here it is exit. Here it is enter at this end, like this. Okay, dear. So the end which is the flux is exit, that is called north pole, and this is called south pole. Now this polarity, the poles will be changed. If we change the here polarity, if this will become positive, this is negative, then direction of current is reverse. Okay. Then this flux also change, means poles will change in electromagnet. But in permanent magnet, these poles are fixed, north, south. Okay. Now strength MMF, MMF, what is the MMF? Sorry, magnetomotive force, FMF per this length of this coil, okay, L, divided by L. So it comes ampere turns Ni by length. It is ampere turns per meter, ampere turns per meter, okay. This is your magnetic strength. It is called magnet. Now this magnetic strength, because by changing the number of turns or by changing the current, if we change the current here, we can change the strength, magnetic strength also. But here, this in permanent magnet, it is fixed. So why we use the electromagnet? Because we can strength we can change, polarity we can change. Okay. Now you got it, hello? So here, this is the flux is upward. Now see, this flux is linked with this primary. So suppose here is N1 turns, here is N2 turns. So there is a E1 self-induced EMF. Okay, E1. Here it is, because this same flux is linked with this coil. So there is a E2. Okay, induced EMF. Now you know E1, E2, we write. Now if we connect the load here, suppose, now at load condition, now if load is there, then okay, there is a load current, I2, secondary current. Due to this secondary current, now this is the direction of current, okay, this side. So again here you apply the right hand rule. Due to this I2 current, there is another flux is set up in the core. Okay, this is opposed. So at no load, there is a no load current, which produces this flux phi naught. I naught represent I. But due to this I2, there is a phi 2 flux. It opposed. Now see, there is a phi 1 earlier, only single flux, phi naught. Now due to this I2, there is a opposite flux will come. Phi 2. Okay, so this load current, as we put the load on secondary, this tends to reduce the flux in the core. But you know, we stated that the magnetic flux in the core, it is constant. For or to maintain the constant flux in core. What happened? This primary draw the more current from source. So this current is increased. Now it become at load, it become I1. Okay. So instead of I naught, now transformer take I1. So this I1 is actually I1 is I naught, no load current, plus due to this secondary load current, what is the component as referred to primary side? I2 dash. Okay, so this will give the full primary current. Now, sometimes the question is asked, when we put the load or we increase the load on secondary, why the primary current is increased? To maintain same flux in core, because due to secondary load, the flux is reduced in core, then transformer draw more current to maintain the same flux. So see, due to this another current, there is another flux is come. That is phi2 dash. So this phi2 and phi2 are opposite and neglify. Then net flux in the core is constant, maintain. Correct? Okay. Now we come to the EMF equation because it is very important. Transformer. As you know, like when we connect the primary to a sinusoidal source, so it produces a changing magnetic flux, correct? So this flux is like this. Okay, this is phi m. Okay, dear. So this induced EMF. Due to according to Faraday's law, E equals to, E is directly proportional to d phi by dt, rate of change of flux, correct? Okay. Then this flux is, phi. Actually, phi is Im sin omega t, as I told, sinusoidal, because sinusoidal current, as we connect the transformer with sinusoidal voltage source, here V equals to Vm sin omega t. Then sinusoidal voltage, there is a sinusoidal current, it produces sinusoidal flux. So here, this is your flux equation, okay? Correct? Now, according to Faraday's law, E equals to this, or E equals to, this is negative. Why? Because Lenz law, d phi by dt. Now, if we put here value, okay, minus n, now d by dt of, please you put here phi m sin omega t. So when we differentiate, it comes minus n phi m sin become cos. Okay. With respect to t we do, then it will be cos omega t, then again omega t become, this omega will multiple. Okay. My dear, this come minus n phi m omega cos omega t. Okay. Now this cos we can write, look, this cos omega t. Cos omega t we can write sin pi by 2 minus omega t. Okay. This we can write. So if we replace this minus n phi m omega, we can write sin pi by 2 minus omega t. Now if we this sign, this minus sign we take inside, then it become n phi m omega sin omega t minus pi by 2. Okay. Now this induced EMF. Okay. This induced EMF per turn we have calculated. Okay. Or in NT. Now therefore E equals to, we can write it is maximum. E is this induced EMF. EMF is maximum when this omega t minus pi by 2 is 90 degree. Then cos 90 is 1. Okay. So we can write this E maximum. Hello. What is the E maximum value? N phi m omega. Correct? Now omega is a frequency. Hello. Omega is nothing but it is the it is frequency in radian per second. So radian per second. So if we put this n phi 2 pi f, or we can write or we can write 2 pi phi m f. Now we can write 2 pi phi. This is the maximum here, maximum flux f n, number of turns. Okay. This is the E maximum. Okay, my dear. So this is 2. Now we calculate RMS value. Therefore, RMS value of induced EMF, that is general induced EMF, E equals to RMS value. Hello, what is RMS value? Maximum by root 2. Okay. So this is 2 pi by root 2. This E maximum value we put here. 2 pi phi m fn. Okay, dear. E equals to, then see, 2 into 3.15. If you solve now, this 2 pi means 3.15. 2 into 3.14 divided by root 2. This value will come, then 5mfn. Okay. So this E is come 4.44. Okay. 5m Fn. It is a general induced EMF. Therefore, it is third. Therefore, self-induced EMF, self-induced EMF in primary, that is E1 equals to 4.445 Fn1. But and the mutual induced EMF in secondary, that is E2 equals to Fn2. So this is 4, this is 5. Okay, dear. Please. So this is the EMF induced in the transformer, the EMF equation of transformer. This is also asked the EMF equation of alternator, back EMF equation of DC general. So please you remember this generated voltage equation or either EMF equation of transformer alternator, you please remember. Okay, this is the working principle and EMF equation. Okay, now please. From now we further go from equation 4 and 5. If this 5 is divided by 4, then 2 by E1 equals to, other things are cancelled, it become N2 by N1. Okay, it is 6. Now, please, you will consider for a loss-free transformer. You know, loss-free transformer is if there is no power loss. It means primary volt ampere. That means apparent power equals to secondary volt ampere. Volt ampere means current and voltage. So V1 I1 equals to V2 I2 power. Or we can write V2 by V1 equals to I1 by I2. This is another relation. 7. Now another you write 4. Now see, at no load, if there is no load, so this current is 0, only primary take is I naught. So this I naught is very less. Okay, I naught is very less. Okay, we can neglect. Like if 100 ampere is a full load current, then no load current is only 4 ampere. Okay, or sometimes it is fraction ampere. So if no load current is neglected, or no load ampere turns, or no load or a magnetizing ampere turns, we can write magnetizing ampere turns, MMF, neglected. In this condition, your primary ampere turns equals to secondary ampere turns. It means N1 I1 equals to N2 I2. Okay, or N2 by N1 equals to I1 by I2. Okay, dear. So actually I1 equals to I naught plus I2, I2 days. Okay, So actually we neglect this current. If neglect, it means I1 equals to I2 days. Actually, actual turn ratio is two, because it is I2 days to I2. Actually, this is this is actual, in actual case, but in practical actually, it means practical. Yeah, but for ideal we consider this. This is for ideal case. These are equal. So therefore, the turn ratio, turn ratio, transformation ratio, K equals to N2 by N1 equals to E2 by E1 or equals to V2 by V1 or equals to I1 by I2. This is the turn ratio. But it is for ideal case. Please. Because here
Sir,
we
what
say
is I2 dash?
I2 dash is the component of secondary load. It is a secondary load current as referred to primary side. Effect of on primary side. Okay. Means secondary current as referred to primary side.
Okay, sir.
Okay, dear. Now we come to the equivalent circuit of transformer. Okay. What is the equivalent circuit? See, as you know, the primary and secondary of transformer, see here, this primary, it consists of wire, so it has a length and cross-section area, so there is a resistance of primary. Then due to leakage flux, there is a leakage reactance of primary and secondary both. And this core is represented by the magnetic core, like in three-phase induction motor, same here. So like there is a, here we write, so single phase transformer, single phase. Now, so there is a primary resistance, then primary leakage reactance. Then this is the magnetizing branch. This represents the core, okay? So this is your primary side, primary. Now we can represent with ideal transformer, here we put this. Then on secondary side, there is a secondary resistance, secondary reactance, leakage reactance. Now suppose it is open, okay? So here this is represented by means primary resistance, primary leakage reactance. So he is asking due to leakage magnetic flux means this reactance is there, okay? Of primary, this is of secondary leakage reactance, okay? Now here, if we apply the voltage V1, primary side, then there is a current is flow, I. Now at this node, there is a no load current. When there is no load, only this current. So see, at no load, if load is there, then there is a second load current, secondary. Now due to this, there is a primary effect means effect of this load current on primary side means here. So at this node, if you apply KCL, Kirchhoff's current law, incoming current is I1. Is sum of I0 plus I2 days. Okay, vector sum it is. Because they have a different angle, phase angle. Okay. So at this node, this current plus this current. But my dear, at no load, this is 0. It means this will be 0. Then transformer draw only no load current. It means here, this is I0. Okay. As we put the load here, okay, dear. Then this is the load. Now maybe load factor means it is an inductive load. Let us we consider a cos phi 2. It is load power factor. It is load power factor, not a transformer power factor. It is load or secondary power factor. It is a load power factor. Okay. Suppose it is lagging, lagging power factor. Okay. Phi 2, this phi 2 is angle by which your secondary current is lagged with this secondary terminal voltage. Now here at no load, the induced voltage is E. Here it is suppose E2. Now at no load, this terminal voltage is E2. But as we put the load, there is a drop here, drop in this impedance. That is known as a Z2. This is known as a Z1, impedance of primary and secondary. Okay. Now, due to this drop, this is reduced. So, which is higher? E2 is higher. At lagging power factor, it is a cos inverse of your. If you do this secondary power factor, then we get angle. Your current I2 is lagged with voltage V2 by this angle. Okay. Then there is this current, and this is I1. Okay, total current at load. So it is at load, full load. Okay, at no load, this I1 is only equals to I0. Okay, dear. Correct, no? So there is a here it is self-induced EMF E1. Okay, this is R0 X0 magnetizing branch component. Okay, now this I0 again has a two component. One is omega, one is mu. Mu is a magnetizing current. This is loss component. Okay, it represents the core loss. Correct? Any doubt here? Now, suppose we this transfer, this, or either we take as we transfer this secondary to primary side. As refers to primary side means we transfer this secondary parameter to secondary side. Then this become and this is secondary resistance, secondary reactance, and this is your load. My dear, here this is your V1, here I1, R1, X1, at this node I0, this is R0, X0, this two component, another component, mu, readable, बड़ा कर लेते हैं. Okay, dear. Then due to this, this is I2 days as referred to primary side. Now this resistance also as referred to primary side, reactance as referred to primary side. E2 also as referred to primary side. But you know already here it is E1, it is the same. It means E2 dash equals to E1. Then here across this load there is a V2 dash. Then here this is load impedance dash. Okay, anything is less? No, no. Now now my dear, see, as I told in motor also, there is a less difference between this, if this magnetizing branch we shift here at load end, this is your I omega. Now this is E1, means across this terminal E1, okay? So it is it. Now here this difference, they are very close, means this V1 is near about E1. So if we shift this magnetizing branch, if we shift this branch here, then no major change. Okay, means less effect in your this parameter. So now it is actual equivalent circuit. Now approximate we are making here. Approximate means your this magnetizing branch we shift to where? At supply end. So just your core loss are change only, because voltage is different. So my dear, here what is the voltage we apply here? V1. To this V1 there is a I1. At this node there is a I node. This is R node, X node. Now there is a two component. This current also I. Now here this see, this resistance, these two are come in series. Okay, these two these two resistance are come in series. Then they have add, no? So they represent as referred to primary side total equivalent resistance, as referred to primary side total equivalent reactance. Okay, dear. And this is your load. Sorry. My dear, what is the voltage here? V2 dash, no? What is the voltage here? Yes. It is V1 only, no? Correct? That is equals to, now it is here V1 equals to E1 almost, equals to E2 days, correct? Now there is a drop in this impedance, because here to current I2 days here. But here we neglect this. We take this load current I1, okay, total, because it is neglected. Now this drop, then it is V2 days. Okay, dear. Now next we can make the same as referred to secondary side also, load side. As this is as referred to primary side. Now as refers to secondary side. My dear, this parameter are shifted to secondary side. In this condition, this is your R1, X1, then this is magnetizing branch. This is secondary resistance, secondary reactance. This is your load. Okay, dear. Now, my dear, here it is as referred to secondary side. Now it is V1 days. V1 days. This is I1 days, R1 days, X1 days, because this is the second primary current as referred to secondary side. This is R2, this is X2, here it is V2. Okay, here it is ZL, load resistance, there is a power factor cos phi 2. This is your I2, load, and here it is I2, not I2 days, I2. Now this is your I naught days. This is R naught days, X naught days, because this also we transfer from primary side. This is also your days, I omega days. Now if we again here, this is your E1 days. E1 days. Here it is E2. Okay. Now if we transfer this, E2 means equals to E1 days. Okay. Now, if we again, if we shift this magnetizing branch as supply and this is your V1 days, because it is this side. Okay, this already we write na, R naught days, X naught days. This is I naught days. Now here it is I1 day. Here it is I2. Now it is total resistance as referred to secondary side. Total impedance. Okay. Now there is a drop, then this is your V2 here. Load side. This is cos phi 2, load power factor ZL. Okay, dear. So this is the equivalent circuit as referred to primary side and secondary side. Okay. Now we discuss the ideal transformer. Hello, please. Ideal transformer. What is the ideal transformer? That is loss free. It means please remember the term ideal transformer means there is a 100% coupling, magnetically coupled primary and secondary, zero, no leakage flux. Means the flux produced by primary, it is 100% linked with secondary. And the coils consist of a high grade conductor. They have a no resistance. So means for ideal transformer, this resistance are zero. This resistance 0 means, and leakage reactance also 0. So this primary and secondary impedance are 0. Okay, R1, X1, R2, X2, 0. Then this core also have a infinite permeability, no core loss, means this branch is also not there. Okay, it means, can you draw here this equivalent circuit of ideal transformer? Hello, at no load. So here if we draw the equivalent circuit, ideal transformer at no load, suppose first we write at no load. Okay, so see, means there is a like primary and secondary. Secondary at no load means no load here. But here we connect this source AC, alternating source. Okay. There is a current is flow at no load. It is I naught, no load current. So my dear, if we draw the equivalent circuit of ideal transformer, you know, this is the equivalent circuit. This is open. Here, this is your primary. So when you apply here V1, it take only magnetizing current. Means your I1 is only equals to I mu only, magnetizing current. No, okay, only this. Got it? So now due to this, there is a induced EMF E1 and induced EMF E2 in secondary primary. Now you know, my dear, this V1 equals to E1 because no impedance, then no drop, voltage drop in primary impedance. Hello? It means V1 equals to E1. What is the difference between V1 E1? After drop, na, only. Which is greater? V1 is greater in practical transformer. E1 is less than because it is after drop. Now, if suppose we put a load, if we connect a load on ideal transformer, okay, then see, induced EMF is E2. Now this terminal voltage become V2. But here they are equal because no drop. So no impedance. Now this is the load current I2. Now it depends what is your load here. Maybe there is a power factor that is lag, lag or lead, or it is resistive, then it is same in phase. But this is the equivalent circuit of ideal transformer. Now let us we discuss at no load only. This current is 0. So see, actually if you see here, you know, this is your sinusoidal source here we apply. Actually, this is your AC source which provide E1. Now after this there is an induced voltage E1. Correct? Here. So when this is a pure inductor, you know, it is like a pure inductor. So as you know now, and see, let us we draw the vector diagram, phasor diagram. Now it is very important, vector diagram. Suppose you take, this is your V1, vertically we take, your V1. Now my dear, in inductor, it is a pure inductor. This magnetizing current is lag by 90 degree, this voltage. This is your magnetizing current, I mu. Okay, it is lag by 90 degree, correct, in pure inductor. It is like a pure inductor when like we connect this. Okay. So your voltage current is lag by 90 degree. Now, you know, this is a magnetizing current. It produces the flux in the core. Now, you know, the flux in, it is directly proportional. Your flux is proportional to current. Magnetizing. So it is, this is the magnetizing flux it produces in the core. Now it induces the EMF in primary and secondary. So now it depends on the number of turns in primary and secondary. So there is this induced EMF E1 and E2. Let us E2, this is E1. They are in same phase because they produce with the same flux. Correct now? My dear, sometimes they ask, this induced EMF are at 180 degree from supply voltage. What is the phase difference between the induced voltage and supply voltage? 180 degree. They are at 180 degree. Okay. This. And they are in same phase both, even it. Okay. So this is the vector diagram of ideal transformer at no load. Okay, when we put a load here, suppose when we put a load in this case, so here it is a V2. Now see, and there is a I2 load current, there is a phi2. So this load current, okay, I am drawing here load current. So this is your load current. It suppose maybe it is a 0.8 lagging power factor. It means this angle will be phi2. This is your I2. Okay, dear. See this below this line, it is secondary side. Now this is primary side. Up. Hello, above this line, it is a primary. This is secondary side. Okay. Correct. So when we transfer this current to primary side, okay, it is here. This is I2 dash. I2 dash equals to, as I told, K equals to N2 by N1 equals to I2 dash by I2, correct? And I2 dash equals to KI2. Please remember, I2 dash equals to KI2. K is the turn ratio of transformer. Now, their vector sum. If we calculate this vector sum, it will give you your primary current. I1. This is I2 day. This is I2 days. Add this now. It is I1. So this plus this will give you I1. Now here at load, this is I1. Okay. So what is your I1? I1 is I mu plus I2 days. And this is the phase difference between this primary current and primary voltage. Phase difference. Phi1. So this cos phi1 will give you primary power factor. Okay? Primary power factor. Okay, dear. Actually, today I think you got a bore because it is totally, concept-wise. But in next class, there is a numerical we discuss on this, and it is very important. Recently, also they asked one question on this. Now, we not take 100% ideal. We just only neglect the primary, secondary impedance only. Okay, magnetizing branch we consider completely. Okay, then we draw the equivalent circuit. Okay, let us we discuss like this. We have a complete magnetizing branch. Okay, dear. It means this I naught has a two component, I omega and I mu. Okay. But other thing, we neglect the voltage drop. Okay. Then if we draw so at no load, when there is no load, transformer only take I naught, no load current. But at no load, transformer is highly inductive. There is sometime why the rating of transformer in kVA, because see, the motor load is mechanical, load on motor is mechanical load. So this power factor is already decided, means the value of motor power factor only. Means power factor of motor that not depends on load. But here in alternator, case of alternator and transformer, load, we put the load, we connect the load, electrical load. Now electrical load may be inductive, capacitive or resistive. It means there is a load power factor. When we connect the load of some power factor, okay, then the overall power factor of alternator or transformer is changed. Okay, that's why their ratings are in kVA, not in MVA, like kilowatt. Okay, correct. So here, because this is the load power factor, So at no load, only transformer coils are there. They are highly inductive. So at no load, the no load power factor. Okay, this is the transformer at no load. It take I naught. Then if we put here wattmeter, wattmeter. We can measure the power, input power. Okay, or by voltmeter ammeter we can measure the power, input power. So you please remember, no load input power to transformer. What is the no load input? I1 I naught at no load, I naught current. Take I naught at no load. When this red branch is not there, it take only I naught from supply. And cos phi naught is no load power factor. And equals to core losses. Hello, open circuit test on transformer, no load test on transformer, it give the core losses. Equals to core loss or iron losses. And it is denoted by IW. Okay, no load power input. Then we can calculate no load power factor. Voltage by I naught. Or phi naught we can calculate, no load power factor equals to cos inverse of this value. Okay dear, it is correct. Okay, when we calculate I naught and cos phi naught, now we can calculate the sin phi naught also. Okay, so it will give the value also, sin cos phi naught. Now my dear, if we connect the load now, when we connect the load on this transformer, then there is I2 in secondary side, load current at power factor cos phi 2, then this become I1. In that case, I1 equals to I naught plus I2 dash vector sum. Okay. So let us check here vector diagram. In this, if we see that this is your primary voltage, applied voltage. Now, at no load, this power factor, it is not a highly inductive. Means power factor is low, means angle is large. This is your I naught. It has a phi naught, large angle. Now, suppose this is your horizontal axis. Now, my dear, this current has a I naught has a two component, horizontal and vertical also. It has two components, this and this. Sorry. Okay, so this is cos side, it become angle side, it become I naught cos phi naught. This is I naught sin phi naught. Means it is I mu, and this is I omega. Okay dear. Core loss. Okay, this you get understand? Hello, this is the two component of no load current. Okay dear, this side. Now due to this, there is a flux in the core. I know this. Now due to flux, there is an induced EMF in primary and secondary. Okay. There is an induced voltage in now. E2 and E1. Okay. Now my T, because there is no drop, then because impedance are not there, then it is equals to V2. Then your load current is lag this I2. Okay, with phi 2. This is I2. Now as referred to primary side, so it current will come this. It is I2 dash. Now vector sum of this two current. Sorry. The vector sum of this two current, it will give you primary current I1. Now angle between these two is phi 1 and this is V1. V1 I1 then phi 1. So my dear, I1 is the primary current and cos phi 1 is primary power factor. Okay. Primary power factor, primary current. Okay. Okay, dear. So today we end here. Tomorrow we discuss the numerical on this. Okay.
सर ये आइडियल कंडीशन के लिए नहीं है ना?
Partial ideal. Partial ideal, and we neglect the voltage draw, impedances only. Okay.
Yes.
There was a one is a 16 mark question is asked on this. I will and now actually one another question they asked. Just I show you. It is in this paper. Yeah, yes. Hello. This is a one question asked here. 10 marks. 230 by 115 volt single phase transformer supply a load of 5 ampere at point A. This is I2 and cos phi 2. Okay. No load current I naught is given 0.2 ampere. At this is no load power factor is given cos phi naught 0.208. Calculate the primary current and primary power factor. So he is asking I1 and cos phi 1. So it is required this we calculate by this this phasor diagram only. Okay. Okay, dear. He give you this. This is 5 ampere. Then this phi 2 we can also calculate because power factor is given cos phi 2. Here 86. Okay. Then I naught also given 0.2. This phi naught also we can calculate because cos phi naught is given 0.208. Okay. Then we calculate the I1 and cos phi 1. These two things he is asking. So tomorrow we discuss this question. Okay. Or either you try. Okay.
सर आपने न्यू सिलेबस कौन से डेट से चालू किए?
First only, no? First Jan.
ओके सर, थैंक यू.
Shayad, I think in 24th also we take a class. We discuss the new question, December question paper.
ओके सर.
Okay. Good night.
सर इंडक्शन मोटर के पहले कौन सा किया था सर?
DC machine.
ओके सर.
सर ये ग्रुप पे शेयर कर दीजिए ना.
चलिए, मुझे अभी एक्चुअली कल इंस्ट्रक्शन आई है कि नहीं डालना है, वो दूसरे ग्रुपों में जा रहा है उनके मटेरियल सब.
सर फिर डेरिवेशन हमें कैसे मिलेगा?
डेरिवेशन तो आपने नोट नहीं किया अभी?
नहीं सर, हम स्क्रीनशॉट ले लेते हैं या तो, है ना?
हाँ, एक मिनट। वो कहिए क्या है, कहीं पर ये सर्कुलेट हो रहा है किसी दूसरे को और है हम। ओके,
एक मिनट सर। ओके सर।